Welcome to a new lecture on artificial intelligence. Today we're gonna study alpha-beta pruning algorithm. In the previous lecture, we studied Minimax algorithm. There was an issue that we called it as resource limitation. So here we are going to study one algorithm in order to tackle the issue of resource limitation. We need to limit the number of exploration. One solution is pruning. Pruning of what? Pruning of our search tree. It helps us to prevent unnecessary computations for the nodes that we don't need to explore. We want to find the branches that have no impact on the policy. Then we do not create them, and hence we can improve the computational cost efficiency. The biggest drawback of Minimax, as we studied, was time complexity. We want to see how we can minimize the time complexity. One solution is not to check all the childs. How? We will see in this example. The blue triangle that you can see here, this is the max. And the value of the first node is based on its children. So you can see here, this is the mean, right? So out of 3, 12, and 8, 2, 4, 6, 14, 5, and 2, we're gonna select the max one. So in the first round, we go for mean, right? Here we check the value of 3. Do we need to check this one? Yes, right? We need to compare. So out of 3 and 12, 3 is the minimum one. Do we need to check this one as well? Yes. So we go and check. So out of 3, 12, and 8, we're going to select 3. In the next round, it's max, right? So 3 will be here. Now we will go for the next branch. The question here is, do we need to check these children or not? If yes, we need to go and check them one by one. If we don't need to check, it means we can minimize the cost, because checking, it means computation, and computation, when we calculate and when we check each value, we compare them, then it means the complexity will grow up, right? So next we go for this one, mean, and C2. Okay, here, do we need to check this 4 or not, right? So you can see here, 3 is already here, 2 is here. The next value has two possibilities. It's greater than 2 or less than 2 or even equal to 2. In case of equality, it doesn't matter, right? So we need to check that whether the next node is greater than 2 or if it is greater than 2, it will not be selected here. Why? Because 2 is already here, and in here we need to value less than 2. If it is less than 2, it will not be selected here, so it's useless. So we don't need to check these two. Okay, so these two are not needed. Once again, when we check this value as 2 and 2 come to here as the mean and here is the max, so 3 possibilities are there for these two values. They are equal to 2, less than 2, greater than 2. For equal to 2, we don't need to check because 2 is already there, right? If it is less than 2, it will not be used here, right? Because 3 is already there. So any value less than 2 will be useless for us because 3 is already greater than 2 and it will not come to this stage. If it is greater than 2, it will not come to this point, right? So it's useless. We are not going to check this one. Let's go for the next one here. So you can see 14 will come here. This is called as pruning, right? It means we saved computational resources by not visiting these nodes. All right, so here we got 14. Again, what is the possibility here? Equal to 14, greater than 14, less than 14, right? If it is equal, we don't need. If it is greater than 14, we will not come to this point, right? We will not come to this point because this is mean. If it is less than 14, still it has the chance to come here, right? So from 14 to 3, for example, if it is 6, if we need it, right, 6 can go here. If it is 5, so we need to go for the next one. 5 should come here. 5 will be here. Again, 3 cases. Equal to 5, greater than 5, less than 5, right? If it is less than 5, for example, if it is 4, it will come to this point, right? Because it's 3. So we need to check this one. Okay, so we need to check this one, but 2. So by min-max pruning, we saved two comparison. So here we're gonna study one algorithm, alpha-beta pruning. So we have a general configuration like mean version. We compute the mean value at some node. Then we are looping over the n's children. N's estimate of the children mean is dropping. Who cares about n's value, the max node? And if we consider A as the best value that max can get any choice point along the current path from the root, then if nodes become worse than A, max will avoid it. So we can stop considering n's other children because it's already bad enough that it won't be played. And the max version is the symmetric to this situation for mean version. So you can see here another example. We have -1 and 3, right? So in here is max, min, max, right? So -1 and 3, we have to compare both of them, right? So 3 will be here. 3 will go to here, 3 will go to here, right? In the next round here, we go for 5, and 5 come to here. The next node is equal to 5, less than 5, or greater than 5. If it is greater than 5, it will not be selected here because mean is already 3. If it is less than 5, it will not be selected here, right? So we don't need this one. The same thing here, 4 is here. We go to this node here, 6 and -4. So out -6 will come to here, -6. Then we need to compare with next one, yes, because it can be like -4. So -4 came to here and -4 is there already. In here, we have a value of -4. The question is, do we need to select these things or not? If it is less than -4, right, it will not be selected here. If it is greater than -4, it will not be selected here. So in this example, 1 is here and 2, 3 is here. So we did pruning. Here is the algorithm of alpha-beta pruning. This is an indirect recursive because one algorithm is going to call another one. We check the value of children for each node. For max, we get the max of children value. For mean, we get the mean value of children. Each node has alpha and beta value. We check whether to continue or not based on these values. Sometimes we don't need to continue and we get out of the loop. So here, we have alpha. Alpha is the max best option on path to root, and beta is means best option on path to the root. So here we go and have this function max value that get state alpha and beta. We initialize with worst case as -infinity, and we iterate through the successors by this for loop. Then we update. So this is a kind of update. V is equal to max of v and mean value, this function of successor alpha and beta. Then if v is greater than beta, we return v. And alpha is the max value among alpha and v, then we return v. In here, we do the opposite side, mean value. We initialize v with +infinity, and for each successor of state, we go for mean of v and max value, this function. If v is less than alpha, we return v, and we update beta as mean of beta and v. This pruning has no effect on minimax value computed for the root. Anyway, the correct value will come to the root. Just here, we are checking how many nodes we do not need to check. So there is a possibility that values of intermediate nodes are wrong. We should care that the children of the root have the wrong value. So the most naive version won't let you to do action selection. It's good to know that by doing child ordering, we can improve the effectiveness of the algorithm. For example, if we do the child ordering, we can get the time complexity from big O of b in power of n to big O of b in power of n by 2. We can have doubles, solvable depth. However, full search of like chess is still helpful. This is a simple example of meta-reasoning. What is meta-reasoning? Computing about what to compute. Another example here, we want to check whether to continue or not using alpha-beta pruning in different branches. Alpha here is the minimum value of node, and beta is the maximum value of node, and v is -infinity for max, right? For mean, alpha -infinity, beta +infinity, v is +infinity, right? Other side. Then again, we do the same for this max, and here is the nodes, right? We start by the worst cases, as I said, and v is the value of each node. If we are at the max node, like here and here, and we check whether v is greater than or equal to beta for the max node, then pruning is there. For the mean node, if v is less than or equal to alpha, then we can go for pruning. So let's try this example. First one is 4, and the next one is 6. So out of 4 and 6, 6 will be here. You can see here alpha is equal to 6, beta is equal to +infinity, and v is equal to alpha, right? Then we go to the next round, and here is mean, so 6 will come to here, alpha -infinity, beta is equal to 6, and v is equal to 6, right? Then we go to the next round here, 7, right? So 7 will come to here. Now the question is whether we need to go to check this one or not, right? Alpha is equal to -infinity, beta is already equal to 6 here, and v value is equal to 7. We say if we are at the max node based on this condition and beta is less than v, then we do pruning, right? So based on the definition that we have, the next node is again greater than 7 or less than 7. If it is greater than 7, it will not be selected in this round. If it is less than 7, it will not be selected in here. So this is one pruning. Then we go and 6 will be here. Then we go for the next. We check 1, so and 1 and 2, yes, we have to check 2. 2 will come to here, then 2 will come to here. So the question here is, do we need to check this part or not, right? If the value representing this 3 is less than 2, it will not be selected here. If it is greater than 2, it will not be selected in this row. So this, we don't need to check this part. Then we go to this part here, 6. So 8 and 1, 8 will come to here. The question, do we need to select this part or not, right? The value of here is either less than 8 or greater than 8. If it is less than 8, like 7, still we have the chance that 7 goes to here. So we need to check this part. So 9 to come to here. But we found the value is 9 here. Again, we check. If it is less than 9, it will not come to here. If it is greater than 9, it will not come to this part. So this one will be out. So totally 1, 2, 3, 4, 5. So we had pruning. We already learned about IDS, Iterative Deepening Search, in the previous lecture. Also, this is known as Iterative Deepening Depth First Search, and sometimes they call it as IDDFS, Iterative Deepening Depth First Search. We already learned that there are 2 ways to traverse a graph, BFS and DFS. Later, we understood that both BFS and DFS are not very efficient for big trees. IDS combines DFS space efficiency and BFS fast search for the nodes closer to the root. How it works, IDS calls DFS for different depth starting from an initial value. In every call, DFS is restricted from going beyond a given depth. So basically, we do DFS in a BFS fashion. Now, we want to see whether we can use IDS for multiplayer games or not. It's worth noting that the wrongness of evaluation function matters less and less the deeper the search goes. In some games, we don't know what the result of an action will be. In this case, we can do Expectimax. We have some chances nodes, like actions expect the environment control the action choose. Also, like before, we have some max nodes. Chance nodes take average, like expectation of value of children. In stochastic games, we don't know what is the result of an action because of many factors like explicit randomness, unpredictable opponents, and actions that can fail. In these cases, the value of nodes should reflect average case outcome. We call the average case outcome as Expectimax Search. It is much better than Minimax, which consider the worst case outcome. So how Expectimax works, we have 10, 10, 9, 100, right? This is called as chance nodes, not min, not max. So what happens here? 10 has the probability of 50 and 10 has probability of 50. So out of them, 10 will come to here. In here, 9 has the probability of 50 and 100 has the probability of 50. So in this case, it will be 9 multiply 0.5 plus 100 multiply 0.5, which is equal to 54.5. Then in this round, out of 10 and 54.5, maximal will be selected as 54.5. So in Expectimax Search, we compute the average score under optimal play. Max node like Minimax Search, but chance node like mean, but we calculate the expectation, right? Expected value. Take the weighted average, right? What I did here is called as weighted average of values of children. So this algorithm is like what we already learned. The only difference here is the probability. You can see here we have the probability. Each children has a probability like 0.5% that we had already. Again, we have an indirect recursion algorithm. 2 functions call each other. The max value function starts with the worst value of minus infinity, right? And then for each children, we calculate V max of V and value successor. On the other hand, we have the Expectimax function. For each children, we have the probability and we calculate the probability. Then in here, we find the V. How? By multiplying the probability in each value, as we did already. Here is an example. So here we have 8, 24, and minus 12. 8 can be selected by probability of 2 by 5, 24 by 2 by 5, and minus 12 by 1 by 5, right? So how do we calculate the value here? 8 multiply 2 by 5 plus 24 multiply 2 by 5 plus minus 12 divided by 1 by 5, right? Which is equal to 10.4. So 10.4 will be here. If the chance is equal for all the final nodes, simply we take the average of the children, right? So there is no probability here. In this case, just 3 plus 12 plus 9 divided by 3, right? Then here, 2 plus 4 plus 6 divided by 3. Then here, 15 plus 6 plus 0 divided by 3, right? Then the max one will be selected here. 3 plus 12 plus 9 divided by 3 is 8. 2 plus 4 plus 6 divided by 3 is 4, and 15 plus 6 plus 0 divided by 3 is 7, right? Out of these 3, 8 is the maximum that will come up. We learn in the probability that random variables represent an event whose outcome is unknown to us. And we learn the probability distribution, that is an assignment of weights to outcomes, right? So probabilities are non-negative. If we sum up them all together, they will become to 1. It means sum of all probabilities is equal to 1. And we get more evidence probability may change, right? So there is one example here. We have a random variable t, and whether there is a traffic like heavy traffic, light traffic, something like that. So t is no traffic, light traffic, and heavy traffic, right? So p probability of no traffic is 25%, probability of light traffic is 50%, and probability of heavy traffic is 25%, right? In the probability, we also learned that expected value of a function of a random variable is the average weighted by the probability distribution of our outcomes, right? For example, we want to know how long it takes time to get to the airport based on traffic conditions. If it is free time, we can reach approximately by 20 minutes, right? If it's no traffic. If it's light traffic, we can go 30 minutes, and it's heavy traffic, we can go to 60 minutes. So we want to travel from airport, from point A to airport. So 3 conditions are there. If it is no traffic, it takes 20 minutes. If it is light traffic, it takes 30 minutes. If it is heavy traffic, it takes 60 minutes. On average, how long it takes time to get to the airport, regardless of knowing the condition of the traffic? 35 minutes. How we find this one? 20 multiplied 0.25 plus 30 multiplied 0.5 plus 60 multiplied 0.25 is equal to 35. Now we want to know what probabilities to use in Expectimax. In Expectimax Search, we have a probabilistic model of how the opponent or the environment will behave in any state. The model can be a simple uniform distribution. For example, rolling a die, you can get 1, 2, 3, 4, 5, and 6, and they have uniform probability, and all of them is 1 by 6. Model could be sophisticated and it may require a great deal of computation. We have a chance node for any outcome out of our control, like opponent or environment, and the model might say that adversarial actions are likely. For now, we assume that each chance node magically comes along with probabilities that specify the distribution of its outcome. In the context of modeling, there are 2 problems that need to be considered. Also, we call them as a false alarm and misdetection. Misdetection, false alarm, or dangerous optimism or dangerous pessimism. In here, there is a problem. There is a problem, but the agent fails to detect it, right? On the other side, in the case of false alarm, there is no problem, but the agent alert that there is a problem, right? And so maybe you can, in psychology, this one is called as overthinking. There is no problem, but the agent thinks there is a big problem. So far, we consider 2-player games, but what if the game is not zero-sum or has multiple players? In this case, we need to think of generalization of Minimax. How we can do it? We can consider terminals have utility tuples, nodes values are utility tuples, each player maximizes its own components, and we can give rise to cooperation and competition dynamically. So in here, you can see we have multiple values for each one, right? Then we have to consider a generalization of Minimax algorithm. Okay, that's all for this lecture. In this lecture, we studied Alpha-Beta Pruning and Expectimax. Please study and feel free to ask me if you have any questions. Thank you and see you in the next lecture.